Hi everyone, myself Dr. P. Ashok Babu. In this video, I am going to discuss about the magnetostatics and Biot-Savart's law. So first of all, how we can generate the magnetic field. We will discuss about the how we can generate the magnetic field. Then we will go for the Biot-Savart's law. So an electrostatic field is produced by a static or stationary charges. Already we have studied in the previous videos. An electrostatic field is produced by a static or stationary charges. So if charge is moving with a constant velocity, a static magnetic or magnetostatic field is produced. I repeat once again, if the charge is moving with a constant velocity, a static magnetic or magnetostatic field is produced. So here a magnetostatic field is produced by a constant current flow or a direct current. So by using a constant current flow or by using a direct current, we can produce a magnetostatic field. So this current flow may be here the current flow, it may be direct current flow or constant current flow. Here the current flow may be due to magnetization currents as in the permanent magnet or electron beam current in vacuum tubes or conduction current in current carrying wires. So by using these three methods, we can generate the current. So here the current may be constant current flow or it may be a direct current. So by using this, we can produce a magnetostatic field. So as a brief, a magnetostatic field is, we can produce a magnetostatic field by using a constant or by using a static magnetic or magnetostatic field, or we can produce a magnetic field by using when charge is moving with some velocity. When charge is moving with some velocity, we can call the field as a magnetostatic field. When the charge is stationary or static, we can call the that field is a electrostatic field. It is a main difference between electrostatic field and magnetostatic field. So here we'll see some analogy between electric field and magnetic fields, just comparison between both electric and magnetic fields. So if we assume electric field, in electric field we'll study the two basic laws. The two basic laws are, first one is a Coulomb's law, then Gauss law. Whereas coming to the magnetic field, here we will study about the Biot-Savart's law. First one, dB is the Biot-Savart's law, and Ampere's circuit law. So this is just comparison. In electric field, we will study Coulomb's law, whereas in magnetic field, we will study about the Biot-Savart's law. In electrostatic field, we will study the Gauss law. So whereas in the magnetic field, we will study about the Ampere's circuit law. So coming to the force law, F is equal to Q into E. Force F is equal to Q into E, where Q is the charge, E is the electric field intensity in electric field. We are coming to the magnetic field. The force F is equal to Q into U cross B. Q into U cross B, where U is the initial velocity of a charge. Next, the source element. Next, third one is source element. Source element we can express in electric field as dq. In magnetic field it is Q into U is equal to I into dl. Q into U is equal to I into dl, where IDL. So in place of IDL, we can use the K into ds, or we can use the J into dV. So it is the surface current density, it is a volume current density. IDL is the line current, where KDS is the surface current, JDV is the volume current. So in place of QU, we can use IDL or KDS or JDV. Next parameter is field intensity. So here electric field intensity E is equal to V by L. So the units are volts per meter. Whereas coming to the magnetic field, here it is electric field intensity E. Here similarly, the magnetic field intensity H is equal to I by L, amperes per meter. Next, coming to the flux density. Next parameter is flux density. The flux density D is equal to psi by S, where psi is the flux, S is the surface area. So it is coulombs per meter square in electric field. And here D is the electric flux density. Same as electric flux density, the magnetic flux density B is equal to psi by S, where psi is the flux, S is the same surface area. And next one is a relationship between the fields. So here the electric flux density D is equal to epsilon E. The magnetic flux density B is equal to mu into H, where H is a similarly electric field intensity. Here H is a magnetic field intensity. And the flux in electric field intensity psi is equal to it is a line integral d into ds. So which is equal to, or we can express it as psi is equal to q, which is according to Gauss law, psi is equal to q. So which can be expressed as c into v, where c is the capacitance, v is the velocity. So v is the potential, v is the potential. The current I is equal to, we can express c is equal to dv by dt. We can express the current as I is equal to c into dv by dt. So coming to the magnetic field, the magnetic flux psi is equal to, it is integral b into ds, where b is the magnetic flux density, and the psi can be, the flux can be expressed as the magnetic flux psi is equal to this q, which is equal to L into I. So here in the electric field, we will use the capacitor, whereas in magnetic field, we will use the inductor. And in place of voltage, in electric field, in magnetic field, we will use the current. So just see the comparison between electric and magnetic fields. So next, coming to the voltage. Voltage V is equal to L into di by dt. L into di by dt. So this is about the flux relation between electric and magnetic fields. Next, coming to the potential. The electric potential E is equal to minus del V. Minus del V. This is the relation between E and V. Electric field and potential. Or we can express the potential V is equal to, it is a line integral rho L dl by 4 pi epsilon r, where rho L is the line charge density, where rho L is the line charge density. Similarly, you can express the magnetic flux, magnetic potential as magnetic field intensity H is equal to minus del into Vm, where the current density J is equal to 0. Or we can express the potential, magnetic potential A as A is the magnetic potential, V is the electric potential. We can express the magnetic potential A as A is equal to line integral mu IDL by 4 pi r, where IDL is the line current, Next, coming to the energy density. The electric field energy density W is equal to half into D into E, whereas the magnetic energy density half into B into H. Similarly, the Poisson equation in an electric field is del square V is equal to minus rho V by epsilon, whereas in magnetic field del square A is equal to minus mu into J, where J is the current density, A is the magnetic vector, here V is the electric vector, A is the magnetic vector. So these are the different comparisons between or analogy between electric field and magnetic field. Now we will discuss about the actual what are the losses available in magnetic field, and what are the different flux relations and applications of magnetic field. So now I am going to discuss about the Biot-Savart's law. So here same as in electric field, if you assume electric field, the total electric fields are governing by the two laws. The two laws are Coulomb's law and Gauss law. Now coming to the magnetic field, so there are two major laws governing magnetostatic fields. The two laws are Biot-Savart's law, then Ampere's circuit law. So first we will discuss about the Biot-Savart's law. So here the statement of Biot-Savart's law is, it states that the differential magnetic field intensity, dH produced at a point P by the differential current element IDL. So here let us assume a differential magnetic field intensity dH and assume a differential current element IDL. So here dH is proportional to the differential current element IDL, and which is again proportional to the sine of the angle alpha between the element and the line joining point P to the element, and it is inversely proportional to the square of the distance R between P and the element. So this is a statement of Biot-Savart's law. I repeat once again. It states that the differential magnetic field intensity dH produced at a point P by the differential current element IDL is proportional to the product IDL and the sine of the angle alpha between the element and the line joining P to the element, and it is inversely proportional to the square of the distance R between the point P and a magnetic element dH. So here it can be expressed as dH is a magnetic field intensity. Here the differential D indicates the differential magnetic field. The differential magnetic field intensity dH is proportional to IDL. IDL is a current element, which is ideal into sine alpha by square of the distance between the current element ideal and a magnetic field intensity, magnetic field point dH. Therefore, it can be expressed as dH is proportional to ideal sine alpha by r square. Ideal sine alpha by r square. So here from the figure we can observe that. So here in figure we have I is there, ideal is there. So it is a where the current element is moving with some velocity, and here the magnetic field is there. So dH is there. So here there are two different conversions for the magnetic field. So here it is, there is some cross. The magnetic field works inside. If there is some dot is there, means the magnetic field works outside. So this is a conversion, dot conversion and cross conversion of a magnetic field. So here we assume a magnetic field dot cross conversion. So here because we assume a dot cross conversion, the magnetic field will work towards the current element or towards the inside. So here the current element ideal is there, and the magnetic field, differential magnetic field dH is there. According to Biot-Savart's law, dH is proportional to the current element ideal and sine of the angle between the current element and the line joining point between the magnetic field and current element. So here let us assume a sine alpha is there. So it is proportional to, dH is proportional to, here it is ideal into sine alpha. And that if you assume the distance between the magnetic field and current element r, therefore it is inversely proportional to the square of the distance between the current element ideal and point P. So this is about the Biot-Savart's law. Biot-Savart's law, dH, the differential magnetic field, dH is proportional to the current element ideal and sine alpha by r square. So it can be expressed as dH is equal to some constant k into ideal sine alpha by r square. So where k is a constant of proportionality, we can assume the k value as k is equal to 1 by 4 pi. Therefore, the equation becomes dH is equal to ideal sine alpha by 4 pi r square. Ideal sine alpha by 4 pi r square. Now, here we can remodify the equation or readjust the equation as. So here in place of ideal sine alpha, so here I am writing the cross product. So here already we have dH is equal to, it is ideal sine alpha is there, ideal sine alpha by 4 pi r square. So in place of ideal sine alpha, I am writing a cross product. Therefore, it is dH is equal to, it is ideal cross AR by 4 pi r square, where AR is the unit vector along the r direction, where AR can be expressed as AR is equal to a vector r by mod r. Is a unit vector. AR is equal to a vector r by unit vector r by modulus of the unit vector. Therefore, the equation becomes, it is ideal cross in place of AR, I am substituting r by r. Therefore, it is the equation becomes ideal cross r by 4 pi r cube, where r is equal to mod r in denominator part. So it is r nothing but the modulus of r, or modulus of the distance between the point P and current element. So here, if we define K as a surface current density. So here L is the line current density, K as a surface current density in amperes per meter, and J as the volume current density in amperes per meter square. Then the source elements are related as, the current elements are related as. So here the line current element ideal is equal to surface current element K into ds is equal to volume current element J into dV. So this is a relation between the different current elements. Ideal is equal to K ds is equal to J into dV. Next, therefore, if you assume these are the moving charge elements, line charge, surface charge and volume charge. Therefore, we can express the Biot-Savart's law by using the line charge, surface charge and volume charges. So here it is, if you differentiate the equation, so already here we have dH is equal to ideal cross r by 4 pi r cube is there. Therefore, if you differentiate if you integrate the equation, or if you apply integration on both sides, so here it is becomes H is equal to the magnetic field intensity, H is equal to, it is line integral, it is ideal cross AR by 4 pi r square, or in another way we can express it as H is equal to, it is a line integral ideal cross R by 4 pi R cube. So this is a magnetic field using the line current. Magnetic field intensity using line current. Similarly, we can find out the magnetic field intensity using the surface current and volume current. So here it is magnetic field intensity using the surface current is H is equal to this is a surface integral K ds cross AR by 4 pi R square, where AR is the unit vector along the R direction. Similarly, for volume current, the magnetic field intensity H is equal to a volume integral J into dV cross AR by 4 pi R square. So this is about the current, surface current, the magnetic field intensity due to surface current, and the magnetic field intensity due to the volume current. So here we can observe the line current, surface current, and volume current from these three figures. So it is a line current along a line, and surface current over a particular surface, and volume current throughout a volume. So by using these three, we can observe the line current, surface current, and volume currents. So this is about the Biot-Savart's law using the line current, surface current, and volume current. Now we'll find out the magnetic field. By applying the Biot-Savart's law, we'll find out the magnetic field due to a straight filamentary conductor, due to a straight line, or simply we can find out the magnetic field by using a straight line or applying a Biot-Savart's law. So here to find out that, now let us assume a figure. So here in figure, the magnetic field, the differential magnetic field is there, or the magnetic field intensity H is there. Here we are using a cross product, means the magnetic field will work towards the inside. Let us assume a current element AB. Let us assume a current element AB which is placed along the z-axis, and assume a current element ideal. Here the current element ideal is located at a distance of z from the origin. So here our aim is we need to find out the magnetic field intensity at point P due to the current element ideal. So to find out the magnetic field intensity at point P due to current element ideal, we need to apply the Biot-Savart's law. So here we'll go through that. So let apply a line current equation to determine the field due to a straight current carrying a filamentary conductor of a finite length AB. Let us assume a total line length will be AB. So we assume that the conductor is along the z-axis with its upper end and lower ends respectively subtending angles due to a straight current carrying filamentary conductor of finite length AB. And here the top end B and bottom end A. So these two will make some angles. So here let us assume some angle alpha 1, angle alpha 2 like that. So these two makes angles alpha 1 and alpha 2 like that. So we assume that the conductor is along the z-axis with its upper end and lower ends respectively making an angles of alpha 2 and alpha 1. Upper end B making an angle of alpha 2 and lower end A making an angle of alpha 1 with respect to the P. Now note that the current flows from point A to point B. So where the current is flowing from point A, where alpha is equal to alpha 1, to point B, where alpha is equal to alpha 2. So if you consider the contribution of DH or differential magnetic field intensity at point P due to a current element DL at 0, 0, Z, because we assume that the current element is the total current element, here it is, ideal is placed at a distance of Z from the origin. Therefore, we can assume the coordinates as 0, 0, Z. Therefore, the magnetic field intensity DH is equal to ideal cross R by 4 pi R cube, where R is the vector. It is a vector. So it is the magnitude of vector. So using the Biot-Savart's law, already we know that according to Biot-Savart's law, DH is equal to ideal cross R by 4 pi R cube. Next, because the line is along the z-axis, assume that DL is equal to DZ. So here to find out that we have a rectangular coordinate system. According to the rectangular coordinate system, we have A into AX or XAX plus YAY plus ZAZ is there. So here there are three unknown parameters. So if you assume the rectangular coordinate system, we need to find out the three unknown parameters. So it is somewhat difficult to find out to eliminate the three unknown parameters using the rectangular coordinate system. Therefore, I am using the next one is cylindrical coordinate system. So in cylindrical coordinate system, we have R is equal to, it is rho A rho plus phi A phi plus Z A Z is there. Z A Z is there. So there are the coordinates of cylindrical coordinate system. So here I am using the cylindrical coordinate system to find out the distance between current element ideal and point P. So here while converting the cylindrical to rectangular coordinates to cylindrical coordinate system, we have rho is equal to root of x square plus y square is there. Therefore, in place of rho, directly I am writing in place of x and y, here I am writing the rho into a rho, where a rho is a unit vector along the rho direction, and in place of z, as it is, I am writing z into az. So here minus is nothing but, so here the magnetic field will flow towards the inside. So because the magnetic field is towards inside, here I am assuming the negative sign here. Therefore, here in magnetic field intensity, DH is equal to, we have ideal cross R is there. We need to find out the ideal cross R. Where R is equal to rho A rho minus Z AZ, and we need to find out the DL cross R. But DL is equal to DZ into AZ. So here I am calculating that it is DL cross R is equal to DL is nothing but DZ into AZ cross. So here in place of R, I am writing rho A rho minus Z AZ. So if you multiply the equation, it is DZ into AZ cross A rho into rho minus, it is DZ into Z into AZ cross AZ. So AZ cross AZ will becomes the 0. Therefore, here we have DZ into AZ cross A rho into rho. Or we can write it as rho into DZ into AZ cross A rho. But we know that AZ cross A rho is equal to A phi. We can write AZ cross A rho is equal to A phi. Therefore, in place of DL cross R, I am writing rho DZ A phi. Therefore, the equation becomes, if we integrate the equation, already we have the equation DH is equal to, ideal cross R by 4 pi R cube. In place of ideal, here I am writing I rho into DZ into D phi by 4 pi R cube. Therefore, if we integrate the equation, we have H is equal to integral, it is I rho into DZ into D phi by 4 pi R cube. You let us assume R is equal to rho minus ZZ. So if you find out the magnitude, it becomes rho square plus Z square whole power 3 by 2. 4 pi into rho square plus Z square whole power 3 by 2. We need to simplify the equation to find the magnetic field intensity. To simplify the magnetic field intensity, so let us assume Z is equal to rho cot alpha. If we assume Z is equal to rho cot alpha and differentiate the equation with respect to Z on both sides. So if you differentiate the equation, so it is dz is equal to differentiation of cot alpha is minus cosecant square alpha. Therefore, dz equal to minus rho into cosecant square alpha into d alpha. We have the rho square plus z square. So rho square plus z square in place of z square. If you substitute rho square cot square alpha, rho square plus rho square cot square alpha, then rho square, if you take rho square common, rho square into 1 plus cot square alpha, which is equal to rho square 1 plus cot square alpha is nothing but cosecant square alpha. Rho square cosecant square alpha. Then if you substitute in the equation, here it is h is equal to minus is there. Already minus is there. So it is minus dz equal to minus rho into cosecant square alpha. Already rho is there. Therefore it becomes minus rho square cosecant square alpha minus rho square cosecant square alpha into I is here. You can keep I by 4 pi outside. Therefore, the magnetic field intensity H is equal to minus I by 4 pi into, if you apply the limits alpha 1 to alpha 2. A makes an angle of alpha 1, B makes an angle of alpha 2. Therefore, we need to apply the limits alpha 1 and alpha 2. So, it is rho square cosecant square alpha d alpha by, in denominator we have rho cube into cosecant cube alpha. Rho cube into cosecant cube alpha. It is rho cube into cosecant cube alpha. Because rho square plus z square equal to, rho square plus z square is equal to, we have rho square into cosecant square alpha. Therefore, if you substitute the equation, we have rho cube into cosecant cube alpha. So, if you simplify the equation, rho square cancel each other, cosecant square cancel each other. Therefore, the magnetic field intensity H is equal to minus I by 4 pi rho into integral of 1 by cosecant is sin alpha. Therefore, integral alpha 1 to alpha 2 sin alpha into d alpha. So, if you integrate the alpha, sin alpha is minus cos alpha. Therefore, minus cancel each other. We have the magnetic field intensity H is equal to, it is I by 4 pi rho into cos alpha. So, cos alpha between the limits alpha 2 to alpha 1. Therefore, the magnetic field intensity H is equal to, it is I by 4 pi rho into cos alpha 2 minus cos alpha 1. Cos alpha 2 minus cos alpha 1. So, this expression is generally applicable for any straight filamentary conductor of a finite length. So, we can assume the semi-finite length or we can assume infinite length also. The conductor need not lie on the z-axis for this particular case. It may be along x-axis or it may be along the y-axis also. Therefore, if as a special case, if you assume the semi-infinite line, so that here the line, the points A, we have A and B is there. Therefore, the point A is at 0, 0, 0. The point A is at origin and the point B moves towards the infinity. Therefore, the coordinates of the points are 0, 0, 0 and the coordinate of B is 0, 0, infinity. Now, the angles alpha 1 becomes 90 degrees because it makes an angle at, it is at the point A is at origin. It makes an angle of 90 degrees and alpha 2 is equal to 0 degrees. So, if you substitute alpha 1 equal to 90 degrees and alpha 2 equal to 0 degrees in that equation is here we have H is equal to I by 4 pi rho into cos alpha 2 minus cos alpha 1 is here. So, in place of alpha 2, it is 0. It is cos 0 minus cos 90. Cos 90 is 0. Therefore, cos 0 is 1. Therefore, the equation becomes H is equal to I by 4 pi rho. So, if you assume a semi-infinite line, the magnetic field intensity of semi-infinite line is H is equal to I by 4 pi rho. Or as a special case, again we can assume the infinite line also. If you assume infinite line, here the coordinates of the point will move towards the minus infinity. The point B will move towards the plus infinity. Therefore, the coordinates of the point A is 0, 0, minus infinity and the coordinates of point B are 0, 0, infinity. Now, the angle becomes alpha 2 is at 0 degrees and alpha 1 becomes 180 degrees. Alpha 1 becomes 180 degrees. Therefore, the magnetic field intensity is, so here it is H is equal to, again, I by 4 pi rho. It is cos alpha 2. Alpha 2 is 0. Therefore, cos 0 minus cos 180. Cos 180 is, it is minus 1. Therefore, it becomes I by 4 pi rho into cos 0 is 1. Cos 180 is minus 1. Minus positive. So, it is plus 1. Therefore, it is H is equal to, we have I by 2 pi rho. So, it is the magnetic field intensity here. Magnetic field intensity due to infinite line. The magnetic field intensity due to infinite line is H is equal to I by 2 pi rho. The magnetic field intensity due to a finite or semi-infinite line is H is equal to I by 4 pi rho. The magnetic field intensity due to a finite line is H is equal to I by 4 pi rho into cos alpha 2 minus cos alpha 1. So, by using these three, we can find out the magnetic field intensity of a straight line, whether it is in z-axis or y-axis or z-axis or y-axis or x-axis. In any axis, we can find out the magnetic field intensity. So, this is about the Biot-Savart's law and the magnetic field intensity due to a straight filamentary conductor. Okay, thank you. In the next class, we will discuss about the applications. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.